So let's go back to the video which we started off with. So we have a pencil and we're not only able to make it move forward, but also we understood how to balance it out. And where is that point wherein we have to hold so that it's balanced. So we learned about center of gravity and center of mass. Center of mass mainly. Then we went on to the movements. So we have learned about straight line, curvilinear, rectilinear, and all of those before the start of this chapter. And in this chapter, we kind of got introduced to circular motion, right? Circular motion. So we are able to describe a object rotating in terms of something called as angle, angular displacement. Then we have angular velocity, acceleration, so on and so forth. Right? In some other chapter, we learned about tangential acceleration versus centripetal acceleration. Right? So we learned all of this. Now we are looking at the cause of such rotation. That is torque, moment of force. So the basic idea is you push on the door. Is it important to consider where you push it? If I have to open a door, say this is the frame and you're trying to open this. And you have the hinges over here, the one which holds the frame and the door. So if I want to open this, say it opens by pushing the other side. So you have to push to open it. So is it important to open or push over here, point A, or can we do it with point B and point C? Which is the most easiest one? Is there, is there any difference between them by pushing at A, B, and C? Is there any difference? Is there a difference? End of it, if you tell, yeah, it opens the door. I'm able to open the door. Okay. Are you putting the same amount of force or different amount of force? That's the question, basically. Answer is there is a difference. Okay. There is a difference. And this force converts your push into because of the structural integrity and the attachment per se, you are able to make it rotate. So moment of force is like a measure of how much that push or a pull makes something want to rotate. So torque is a tendency for a force to cause or change a body's rotational motion. It is measured as the product of magnitude of a force and the perpendicular distance between the line of action of the force and the axis of rotation. Okay. So this we will go and take up a diagram. Say I have a nut and bolt situation and I have something to open with, say, I can do a better job though. Say I have okay, looks okay. I'm trying to draw a adjustable spanner. Doesn't matter actually. Spanner. Basically, I have a spanner. And it has a arm in this manner. Okay. Now, so you have this to be your center. So say you are pulling it over here. Say you're pulling it over here with this angle and everything. And as a reference, I'll just draw a straight line over here and say this is angle theta. Right? So if this is the force F, do you think all the force is used to opening this nut or closing this nut, whatever we are doing? In this case, so technically it would be, just a second, I'm trying to rotate it to the top. It will open. Okay, we are trying to open it. Okay, so is all my force going into opening the nut? No, right? What's happening? Some of the force will be wasted and some of the forces will be used. So for that, I will make use of resolving of vectors. I'm resolving one along the line connecting the centers and one perpendicular to this line. Now, according to you, which will help me? Will F cos of theta will help me open the nut, or F sine of theta help me open the nut? This is your radial, because it's along the radius, it's along the line connecting the centers. This is your radial component of the force, right? And this is known as tangential component. It makes sense, right? Tangent. Will tangential component, because I'll start using these words, okay guys? Will the tangential component, we can call this as f of t, will that help? Or our radial component, I'll call this as f of r, which will help in opening nut, right? This is the winner. This helps in opening the nut. Okay, so basically it's okay. Let me go to the definition. Torque it is a measure of the product of magnitude of the force and the perpendicular distance between the line of action of the force and the axis of rotation. Okay, let me go word by word over here. Which is your axis of rotation? Yes, so let me take up this. That's our axis of rotation. You guys agree? Now, the perpendicular distance between that and the force. So to get that, what should I do is, I should extend this line and pick a point which is wherein they are perpendicular to each other. So basically, so technically, if this length represents, this direction and everything represents S, if this is R, this length will be R sine theta, because this is vertically opposite angle. So this is theta. This length is R, this is hypotenuse, and this is your adjacent side, opposite side. Do you guys agree? This is R sine theta. This is that length which the statement is talking about. This is that perpendicular distance between line of action. So what is your line of action? This is your line of action and the axis of rotation. And the axis of, wait, I think line of action is not that. Axis of rotation is this. This is line of action. Yeah, this is line of action. So line of action is that infinite line that lies along force. So along this line of action, this is a perpendicular distance between the line of action and the axis of rotation. So this is your axis of rotation. I mean, of course, axis of rotation is coming towards you. I can't draw this. So from the axis of rotation, if I draw a perpendicular line to the line of action, this distance matters. The force and this distance is the key. Okay, so basically, torque is a combination of this force and this line, this length. Okay, this perpendicular length. That's the perpendicular distance. Okay, so this line is the perpendicular distance. So it is measured as a product of magnitude of force. Yeah, magnitude of force. This. So if I multiply with r sine theta, I'll end up on rearrangement, I'll get f sine theta. Okay. So torque is represented with tau. So if I multiply F with, or actually you need to practice this, F R sine theta with F, I can rearrange this as R into F into sine theta. And sine theta is the one which is contributing to the rotation. So that's your tangential component. So end of it, you will get back that formula. Okay. Yeah. So where was I? We're looking into the concept of torque. So mathematically, as a formula, I just showed you guys. So this is your magnitude. So let me introduce it to you guys properly. So here tau is read as tau is the magnitude of the torque. Then R is the distance. So these are important, okay? From the, see guys, point is how far away are you from the pivot is important. Where the force is applied. So this length plays a role. This length plays a role. Larger the value of R, better it is for us. F is the magnitude of applied force and theta is the smallest angle between vectors R and F, right? So vector R and F, this and this vector, this and this vector. Okay, again, they're just the direction that we are looking at. So this is your magnitude form. So this is your formula of torque. Formula for torque in magnitude form. There is direction also because this is a vector quantity. We'll look into direction next. Next, there is something called as lever arm form. And this is also as a scalar product, R perpendicular times of F. So this is the perpendicular distance. R perpendicular represents the perpendicular distance, aka lever arm from the pivot to the line of action of the force. So yeah, in this case, sorry, it's a bit messy. Now it's okay, I guess. So in this case, what is your lever arm? Where is that? We have our lever arm. This is your lever arm. Okay. So this is your lever arm. Okay, so that's our lever arm. Next, we have your component form. So basically, if I have R, let me write it here itself, Rx I cap, plus I'm going to write that 3 dimension. So 2 dimension will be simpler. Rz k cap. Then we have your force along the x-axis, along the y-axis, and along the z-axis. If it's so, then your tau will be tau x I cap, actually tau is tau na, plus tau y j cap plus tau z k cap. But how do you find tau of x? Tau of x will be ry fz minus rz fy, and tau y will be rz where does this come from? Sorry, I think I will make it clear by writing the next form. Rz will be Rx Fy minus Ry Fx. Okay. So again, I have the formula in front of me, so I'm able to write it easily. Okay. So I'm not memorized this. So determinant form is what I can comfortably write. I'm sure you will also be able to write this determinant form. So you can get, oh, sorry, I don't have space over there. End of line. So I can get the formula by just doing this, finding the determinant and writing Rx, Ry, Rz. I hope you guys, you might have not, no, you would have not done this. Matrix, I have not advised you guys to do it actually. Yeah, this is one thing that, no, wait. No, you won't be, you would have not done it. So this is one more form that you have to learn a topic called as matrix to understand this. Okay, yes. So basically what you're doing is here a cross product, right? From this you should have known this leads to cross product. Okay, so all of this leads to cross product. If you understand dot product and cross product well, this formula is nothing but your AB sine theta. So A cross B. Okay, so from that, let's look at the magnitude component form, determinant form done. Role of the angle. When do we have the angle to be maximum? So for what value of theta you have things to be maximum? For what value of theta 2 is maximum at? Correct. Theta is equal to 90 degree. Means what? If I want to open something, it's best done by applying a force at 90 degree. And 2 is minimum at theta is equal to 0 degree. Sine 0 is 0, right? So basically, if I have to rotate something over here in this direction, but I'm applying force in this way. If I'm pulling the door, right? If I pull the door, not that way, as in if this is the door. Okay, so if someone is pulling in this manner, are you getting it? You're pulling it, so what will happen? Nothing will happen. If I pull it, yeah, I mean, you might damage the door itself. If not, nothing will happen. So this is space for your maximum and minimum. Then what do we have? Role of R. So role of R, by doing it practically, it will be easier to understand. If I have something to open, is it better that apply 10 Newton of force over here or over here? If I want to rotate something, it's better to apply here. If you look at your screwdriver or your wrenches and all of that, like lever and all of that, so what do we have? We have it to be further away from the pivot. Further away, better it is. So if I have something, a screwdriver or a spanner, right? Longer the arm, better it is for me, right? Longer is better. It makes our life a lot easier. So R more is better. And you can look at it mathematically also. T is R F sine theta. If this is constant, right, then it is priority proportional to R. So if this increases, this increases. Mathematically also, you can see that. Of course, you can do it physically also. If you have to lift something, right? If you want to lift something, and if it's heavy, it's better to place it using a long arm. I mean, place it over here with a long arm at the other end, and you hang on to it. Okay, could have done a better job. Okay, let's just hang on to it. Not a good idea. It might break, but still, if you want to get the best force possible, this is the best case scenario. Okay, that's how you can get R to be maximum. R is maximum when you have it further, minimum when it is over here. So you're applying a force over here gives R to be 0 and tau to be 0. That's the minimum. Case of minimum. What else we have? Yeah, direction of torque. It is determined by the right hand rule. So first is you need to point your finger along R, curl your finger in the direction of F, and the thumb points in the direction of toe. So basically, so you are trying to turn something over here. Your R is along this line. Your force, say anywhere, it can be anywhere. So it's over here. And if I take my right hand, if I point first, I should point in this direction. So I'm pointing and I have to curl my fingers in this direction. I'm curling, my thumb will point up. Did you guys do that? So your hand should look like this. Out of the screen actually, basically. So technically it would look something like this. I could have done a better job. I think this is okay. Not exactly, but yeah, I think better. So it is pointing outward to the screen. So in this case, it is outward. Okay, here, let's do it here. So the R is pointing away. So my finger is there. And I'm trying, my force is downward. So pointing away and downward. I mean, downward as in, downward only. So my torque is inward. It's pointing that direction. That's the direction of my torque, right? So force is inward. So my hand goes like that and my fingers are curled that way. So basically my hand is looking like this. Again, guys, you have to do it. Me drawing it and showing something over here will not help. Confirm it. What if I'm wrong, I'm telling something and I'm using my left hand. So try it. That will be the direction of torque. That's it. So in this case, again, I'm not able to write it exactly because it's inward and this is upward. So you guys should conclude on your paper. Example, if a force causes counter rotation, toe points out to the plane. All this statement you have to confirm on your own. Now, finally, on small note, torque obeys superposition theorem, like all the forces. When several torque acts on a body, the net torque is the sum of the individual torques. Okay, so all of that is possible. Now, what did we learn in this video? So to this point, actually, we learned about rotational things. So when can I rotate this? What is the best way to rotate it? See, when I'm hitting over here, see how did I hit? At the end, okay, right? And I'm hitting perpendicular to the length. Perpendicular to the length. So that all of this added up is known as moment of a force or torque. So moment of a force is like measuring how much of a push or a pull makes something rotate. So torque is a tendency for a force to cause or change body's rotation, rotational motion. So it is equal to the product of magnitude of force and the perpendicular distance between the line of action of force and the axis of rotation, right? So we saw that exclusively. Okay. Then we are looking at the formulas. So there are many forms. So basically this is a cross product scenario, but anyways, I've shown only the magnitude over here. When we apply it, it will make more sense. Then the lever arm form, component form, and determinant form. And we saw the maximum and minimum when theta makes things maximum and when it makes minimum. When does R make maximum and when does R make minimum? All this kind of commonsensical. You do it practically, you'll get to know. Direction is given by right hand rule. You have used it in many scenarios, starting from your 9th and 10th grade electricity also. You guys would have used 8th or 9th or 10th. Previous grades, whenever you have used. So the same thing follows over here. And torque, like any other forces, we can add up and look into only the net force, net torque. Right? So now is the time for you guys to pause, copy. Whatever you feel like, copy. Next, mathematical torque and magnitude. So that would be the heading, and these are all the formulas. And when it comes to next is when it comes to theta being maximum and minimum. And when it comes to R being maximum and minimum. And the direction of torque, you have to write this. And give yourself an example. And a small note.